Okay, so yesterday we talked about a confidence interval for a difference between two proportions. And now we're going to talk about how to do a hypothesis test for a difference between two proportions. Okay, and we're going to use the same example of the resumes that were sent out. 2,445 commonly white name resumes, 2,445 commonly black name resumes were sent out to various employers, and the callbacks were 246 for the white name resumes, 164 for the black name resumes. And you can see just that information above is in this table here. So this is just basically a clone of what we did yesterday, where we need some quantities and some calculations. So N1 and N2 are both 2,245, the sample size of each, the white name resumes and the black name resumes. Okay. The proportion of white name resumes that received callbacks, again, we did this yesterday, was 246 out of the 2,445 sent out, which gave us a proportion of 0.101 or about 10.1%. The proportion of commonly black names that received callbacks, 164 out of the 2,445 that were sent out, and that worked out to a proportion of 0.067 or about 6.7%. And then the difference between those two sample proportions, that's white minus black, would be 0.101 minus 0.067, which gives us 0.034. And we talked about below, it's the same answer in the previous lesson, okay? So in a world where we assume there's no discrimination, what are the chances that white sounding applicants would get 3.4% more callbacks? Okay, well, could have happened by chance alone. Seems to suggest that white name applicants got more, were preferred to black name applicants, but we don't know for sure, so we need to study it more statistically. Could have risen by chance alone, maybe not. More study is needed. Okay, so yesterday, or in the previous lesson, we set up a confidence interval, or we calculated a confidence interval, where under certain conditions, it was a normal distribution. We found the average if we took several samples and subtracted p hat 1 minus p hat 2, and then we found the standard of error of that. And then with 95% confidence and a normal distribution graph, we were able to figure out the confidence interval. Okay. For a hypothesis test, remember, we want to state the null hypothesis or the status quo. And then we want to state the alternative hypothesis, what we're trying to prove. Okay. So in this example, the null hypothesis, or HO, the employers don't discriminate. Okay? Don't discriminate. Just got it by chance. That's what we are going to assume is true. And then numerically, we could say the proportion, and remember this applies to the population now, the proportion of callbacks for white will equal the proportion of callbacks for black, because there's no discrimination. They equal each other. But then the claim, the alternative hypothesis, is that employers favor white applicants. Okay? It's unproven as of yet. We need evidence. And that's where the statistical calculation comes in. And using mathematical notation, if it's favored, that means the proportion of white name resumes would be greater than the proportion of black name resumes. Okay, so for the null hypothesis, it's the same in both groups. And the alternative hypothesis is that there is discrimination, in which case the commonly white names received a higher rate of callbacks. So remember, when you are doing a hypothesis test, regardless of whether it's one proportion or two proportions, we have to state HO and HA mathematically, and then we have to say what the variables represent. So P1 is the proportion of white applicants, but commonly white names who got a callback. P2 is the proportion of black who got a callback. Okay. We're trying, and remember, we're taking our sample and we're trying to see, we're applying it to the population. Now, instead of writing it like this, we normally would write it when we do the null and alternative. We would say, if we took the difference between the two proportions of callbacks, it's nothing, meaning no discrimination. The alternative that we're trying to prove is that there is discrimination, which means if we subtracted the white by the black, it would be greater than 0. And we've got one sample to deal with that we took, right? And we need to see if the probability of getting that sample, or even higher, 0.034 or even higher, is it really low, which means we couldn't have just got it by chance alone? Or is it normal that we could have got it by chance alone? And that's where the alpha level comes in, that significance level of 5%. Okay, so like we did with confidence intervals, but we do it different with hypothesis tests, because remember, confidence intervals, we're using a normal distribution to create the confidence interval. With the hypothesis test or significant test, we're using the normal distribution to find the probability of getting our sample, or greater or less, depending on the question. Okay. So right now we start by assuming the null is true. Okay, there's no discrimination, all that rates are the same. And we ask ourselves, if in a world where the null is true, how likely is the data we got on the first page? Okay. So we want to see what happens with multiple trials. If we did several trials and took the sample proportion of white names minus the sample proportion of black names, and we get a whole bunch, and we found that it forms a normal distribution, and it's centered around some value, okay? And then we use our sample to figure out, okay, how is our sample sort of within this, or is it out here somewhere? And given the way I've drawn this graph, you can probably guess where it's going to be. Okay. So remember, we're assuming the null. where P1 minus P2 is equal to 0. Therefore, this is 0. That's our mean of all the sample proportions we took, of all the trials that we did. Because we're assuming it groups around 0. There's no discrimination. Okay? So remember, under certain conditions, and we'll talk about those conditions later when we do the full solution to this problem. Okay? The difference in the sample proportions takes a normal distribution. The mean of all of these will equal the null value. And remember, the null value was 0, no difference. So that's why we put 0 here. And then we have to find the standard error to figure out the number of standard deviations away. And then it's a very similar formula to what we did yesterday with confidence intervals. Remember, confidence intervals, we took p hat 1 times 1 minus p hat 1 divided n1 plus p hat 2 times 1 minus p hat 2 divide the sample size of n2, square rooted that, added them together and square rooted that. We do it a little bit different with hypothesis tests, and you can see that we've got something called p hat c. Okay? So since the null hypothesis assumes there's no discrimination, so they equal each other, or if we subtract the white minus black, we get 0. Okay? We combine the proportions. Cut callbacks. Into one estimate. One estimate. And we call that P hat C for P hat combined. Okay. So this is the combined proportion who got callbacks. And how do we calculate it? We calculate the combined proportion who got callbacks in the samples that we took. Remember, it's P hat. By adding the number that received callbacks in both groups. So for white, it was 246, and for black, it was 164, over the combined sample size. And remember, it was 2445 for each. That's how we find P hat combined. So when we do this, we're going to get approximately 0.084. That's the combined proportion who received callbacks. Okay. It's almost, I don't know if I should say this, it's almost like an average of the two. Okay. Because remember, it was like 10% for the white, 6%. So it's somewhere in the middle. That's how we do that. So that's how we get this, is we take, now that we've got this as 0.084, we take 0.084. Actually, I'm gonna write it down here. Space. Take 0.084 times 1 minus 0.084. Divide the first sample size, which is 2445, plus, and it's going to be the same thing again, 0.084 times 1 minus 0.084. Divide the sample size of the second one, which happens to be the same as the first one. So when we calculate all of these, when we calculate this and this, add them together in square root, we get approximately 0.079 for our standard error. That allows us to complete the distribution above. So now we know the standard error. So it's going to be adding 0.0 0.0079, 0.0158, 0.0237 for the three to the right of the mean, the difference in the sample proportions. And remember, we would label this horizontal axis. It's the difference in the sample proportions. And then we would go 0 minus 0.0079, so we get negative 0.0079. And then we would get negative 0.0158. And then we would get negative 0.0237. Okay. Now, right now, you can kind of look at this. What was our sample difference? 0.034. That's what we got. Where would that be on this normal distribution? Way out here, right? So that seems to suggest right away that, oh, the probability of getting that is really low because it's like completely outside the normal. We would have to go even more standard errors to figure out where it is. Okay. So that seems to suggest that the p-value that we're going to get, because remember, it's the p-value that determines our conclusion to the hypothesis test, is going to be really, really low. Okay. So this just kind of summarizes what we did on the previous page. I'm just going to do this very quickly. It's the same thing with the same numbers. So it's 0.0079, 0.0158, 0.0237. But if I extend it and keep adding 0.079s, I'm going to get 0.0316 and 0.0395. Remember, ours was 0.034. So our sample difference was way out here. So 0.034 would be somewhere around there. So if we extended this, and remember, it would just keep getting smaller and smaller and smaller. There's our p-value right there. That's our p-value that we have to calculate. That's the probability of getting the sample difference, which you can see is going to be really, really low. So we're pretty much to the point where we can say, well, that p-value is really low. We didn't get that just by chance alone. We can say that there's convincing evidence that white names do receive more callbacks than black names, and therefore there's possible discrimination taking place. Okay, but we do have to. So remember the way that we calculated it. This is sort of the long way, and then we'll go back and do the shorter way with the graphing calculator. We had to find a z-test statistic. So we had to find basically how many standard errors were we away. Okay. And if you remember, and maybe you may not, this goes way back to Unit 2 when we calculated z-scores, where we did mean. I say this because it's the same setup. Mean minus data value over the standard deviation. But remember, in our example, in what we're doing here, the mean, okay, or sorry, I don't have that right. Isn't it? It's data value. I don't think I have that right. Is it data value minus mean? Yes. That's what I was saying. So it's that. That's data value minus mean. That tells us how many standard deviations the value we got is away from the mean. So remember, our data value was the difference we got in our sample. The mean, well, it's the average you see above. It was 0. It's what we assume is going to be the mean under the null hypothesis, no discrimination. So the difference would be 0. And then instead of standard deviation, we used the standard error that we calculated. That was 0. How many zeros? 2. 0.79. And that gives us about 4.3, which you can see on the graph fits because we are about 1, 2, 3, 4, and a little less than half standard deviations or standard errors away from the mean. And then the p-value, and again, remember, I'm talking about sort of the longhand way of doing it. How do we find the probability of getting this or greater? That's when we use normal CDF. So normal CDF, our lower boundary is 0.034. Our upper boundary is a ridiculously high number. So let's put 1,000. Our mean is 0. And our standard deviation is the standard error, which is 0.0079. And when I plug all that in, I am going to get approximately 0.40. Again, it fits. Everything, it's really low probability of getting that, or even higher. Okay. So to interpret, okay, the Z statistic tells us our sample difference is 4.3 standard errors away. I'm just put SCD for standard errors away from the null value, the assumed value, which we said 0. And you may want to take a note of the interpretation of the p-value, because there was a challenge with interpreting this on test that you guys just wrote. Remember, the p-value represents the probability of getting our sample proportion, in this case sample difference, or greater, assuming there's no discrimination. So in a world where there is no discrimination, so that's the null, probability of getting our sample difference proportion sample that we're working with, or greater is 0.401. Okay. And because that's so small, and you guys that are familiar with this, we can draw a conclusion in a world where there's no difference, the null, the observed data, is highly unlikely. The p-value equals 0.401. So we reject HO. I'm just going to shorten that. I know I left more space. But we reject HO. We reject the null hypothesis and state there is convincing evidence that commonly white name resumes receive a higher callback. And then they're saying that because of that there is discrimination. Now that can be a little iffy because maybe there's something else causing this. Okay, so I don't want you to, I hesitate. I mean, it's a good example, but I hesitate to go from, because there's more higher callback rates, there's discrimination. Okay, there very well could be, but maybe there's some other stuff in there too. So this connects with what we did yesterday. This is what we did in yesterday's lesson. We found the confidence interval. This is what we did today. Okay. And we can come to the same conclusion because yesterday, remember, the confidence interval we got, all the differences in the confidence interval were greater than 0. So we were able to say, because there were no negative differences, white names receive higher callback rates. That's what we concluded from these. And then you know what we just concluded from these. So does the interval provide? Yeah, of course, yes. Because all differences, and when I say differences, I mean white minus black, are above zero, greater than zero, however you want to say it. Okay. Okay, let's just put it all together now. And just like we did with confidence interval for one proportion, hypothesis test for one proportion, confidence interval for two proportions from yesterday, we can do a four-step process. We have a graphing calculator function that will do all the work for us. We don't have to draw those normal distributions. We don't have to calculate the z-test statistic. It does it all for us. So same problem, right? Here's how we set it up. You know how to set it up. State, plan, do, conclude. So remember the state. That's where we put these. And then what each variable that we state represents. So the null hypothesis would be that no difference, P1 minus P2 is equal to 0. If we were to subtract the white names by the black names. Alternative that we're trying to prove, there is a difference. It's greater, more white names. And of course you have to define them. P1 is the true proportion. Of white names without callbacks. And P2 is the true proportion. Black names. Without callbacks. The plan. We are performing a two-sample z-test. Remember, when it's proportions, we use z. And because it's a hypothesis test, we use test. If, and then the conditions. I should say performing a two-sample z-test for P1 minus P2. Not a huge deal if you just put that in. Okay. Random, well, this names were randomly assigned, right? Sorry, residential randomly assigned. Residential randomly assigned. 10%. Well, normally we take the sample size and see if it's 10%, less than 10% of the population. If it's an experiment, we don't need to verify. Because it is an experiment. But the large accounts, we do have to do some calculation to show that it's a normal distribution, which allows us to do the calculations we're going to do. Okay. Now remember, we have to use this, a combined sample proportion, and we calculated it to be 0.084. So we have to do 4 calculations. Fortunately, it's going to basically be 2 are the same and the other 2 are the same. So remember, we have to do the first sample size, the number of white, or the number of white resumes, the total number in the sample, times the combined sample proportion, and then N1 times 1 minus the combined sample proportion. And then we have to do it for the second group, the commonly black names. But if you notice, this is going to be 2445 times 0.084. And this is going to be the same thing. So it's going to give us the same answer because it's the same sample size for both groups. And then these 2 down here are going to be the same calculation. 2445 times 1 minus 0.084. Same calculation here. 2445 times 1 minus 0.084. So when we do those calculations, we're going to get 205.4. If you did 205, if you rounded it, that's fine. Obviously, we're going to get the same for this. And then when we do each sample size times 1 minus the combined proportion, we get 2239.6. Means this is going to be the same answer. And then I'm just going to write under here, all greater than or equal to 10. So we're good. We can do the calculations that we're going to do. Speaking of calculations, at the do phase, oh, here's the calculator steps. Okay. Got 2 samples, and we're doing a test. So it is a new one. 2 proportion Z test. So when you go to that function, it will tell you what to enter. It's going to tell you to enter the number in the first group that received callbacks. And remember, these are the white name groups, so 246. Sample size of the white group was 2445. And then it's going to ask for the same information for the second group. The number of black names that received callbacks was 164 out of a sample size of also 2445. And then here, this is very important. Remember, this is what we're trying to prove, that P1 is greater than P2. Okay? We don't want to put equals, we don't want to put less than, or sorry, not equals or less than. Otherwise, we're going to get a completely different number. And then when you do that, actually, I've got it here. It'll give you that Z-test calculation that we did, which was very similar to what we did. But the one that we want to focus on, and remember, it's not the p-hat value, it's the p-value. So that's the p-value, and it was approximately the same as we got when we did it longhand. Okay. And then remember how we conclude the test? Because our p-value is less than what normally is the significance value or alpha value of 0.05 is less than the alpha value you reject the null. You reject HO. We have convincing evidence no white machine resumes. Receive callbacks. So what it really comes down to this unit 7 is we did 4 major things. We did a confidence interval for one proportion. We did a confidence interval for a difference between 2 proportions. We did a hypothesis test for one proportion. We did a hypothesis test for a difference in 2 proportions, which we did today. Each one of those has its own function on the graphing calculator under tests. You need to be familiar with which one is which. Now remember, to figure, like, first of all, you have to determine when you get a question, is it confidence interval or is it hypothesis test? Well, look at the question. It's going to ask you to construct a confidence interval. That tells you that we're going to do the confidence interval thing. Okay? If it says, is there convincing evidence of something? Remember, we talked about that before. That means a test. And it should also be obvious in the question if it's one proportion or 2. Okay? Because if it's one proportion, they're only going to give you 1. If it's 2 proportions, they're going to talk about 2 groups. So that's the first thing. He's got to figure out which one of those 4 is it going to be. That was the majority of what we did in the unit. Some of the extra stuff that we did was the type 1 and type 2 errors and the power of the test. Okay? But that's basically what it comes down to. So in the next unit, we're going to do the same thing, the same 4 things, except we're no longer talking about proportions. We're talking about means. So things like average salary, average age, something like that. Okay? Whereas in these ones, we are always like proportion who favor this, proportion who prefer this, the proportion who did this. Okay? So we're going to have, the other thing we're going to have to do when we finish Unit 8 is differentiate, is it a proportion problem or is it a mean problem? Which we'll have hopefully plenty of time to practice. Okay.